Welcome back. This is Unit 9.2. We're going to talk about the strength of acids and bases. And again, this is found in Chapter 17. All right, so an introduction. Remember a couple of sections ago when we talked about the solubility or the insolubility of salts? We called that slightly soluble because we said there's really nothing that's totally insoluble. And we used the ice charts. And some salts like NaCl dissociate completely 100%, while others like PbCl2 don't. Well, the same principle applies to acids and bases. And we talked about in our last section the acids and bases that dissociate 100%. They're called strong acids and bases, while there are those that don't dissociate 100% and they're weak. So if it's not on the list of strong acids and bases that I gave you, then consider it a weak acid or base. It's just that simple. All right, and so let's review the strong acids and bases that we have. Okay, so for the strong acids, it's going to be hydrochloric acid, hydrobromic acid, and hydroiodic acid. So these are the three halogens that are strong, and there's three polyatomic ions that make strong acids, and that's HNO3, HClO4, and H2SO4. Okay, so those are the strong acids. Now, strong bases, it's going to be any group 1 metal except the top one and the bottom one, francium. Okay, so that's going to include, of course, lithium, sodium, potassium, rubidium, and cesium. Okay, and remember, bases all have OH on them. Okay, and it's all group 2 except for the top two, which is beryllium and magnesium, and the bottom two, which is barium and radium. Okay, so that's going to be calcium hydroxide and strontium hydroxide. Okay, so those are the strong acids and the strong bases. Make sure that you have those memorized. All right, so when we talk about these strong acids and strong bases, we look at combining them with water, and then we have what's called a dissociation or an equilibrium constant equation. So remember in our last section we had KEQ, right? And we did products, the concentration of the products over the concentration of the reactants. Okay. Well, we're going to do the same thing here. And remember, we don't include liquids and we don't include solids in these equilibrium expressions. So here we have this equilibrium expression where we're taking an acid and we're mixing it with water. Okay. Now, in our last section, we saw that this would be H3O, okay? And I just want to tell you that most of the time you're not going to see it written as H3O. See, the water is gaining this hydrogen. You're not going to see that very often. Technically, that's what happens, but you're going to see it written like this, just as a hydrogen ion, okay? And then here's the anion or the conjugate of this acid. Okay, so we're going to take, this is aqueous liquid, so we're not going to include that aqueous. So we're going to take our products. Okay, so it's going to be the concentration of the hydrogen ion times the concentration of the conjugate base over the acid. Okay, so this is the Ka expression, just like the KEQ or the KSP that we did in our solubility of salts. Same exact thing. Okay, so we have the same thing here with the base. NH3 is a base, it's ammonia. And by the way, it's a very common example in chemistry of a base, a Bronsted-Lowry base. NH3 combining with water produces NH4, so the water is going to donate to the base is going to accept the hydrogen, and then what's going to be left over when we take a hydrogen off is just your OH. Okay, so same thing, writing the Kb expression. Now it's Kb because this is a base. We're going to leave out the water. So it's going to be the concentration of NH4 times the concentration of the hydroxide ion over the concentration of your Bronsted-Lowry base. Okay, so writing the KEQ for those. All right, so for the strength of Bronsted-Lowry acids and bases, when acids and bases react together, the equilibrium is determined by the strength of the acid base involved. If the KEQ is greater than 1, then the products are favored. And if the KEQ is less than 1, then the reactants are favored. So you just have to look at the KEQ to see which direction the equation is favored. So another important fact, stronger acids are more able to donate your hydrogen ions. So the position of the equilibrium is determined by the stronger acid base reacting. Okay, so here's an example. So we have NH3, which is going to be our base. Let's go ahead and label that. Okay, and this is going to be our acid. Okay, this is going to be our conjugate acid. And this is going to be our conjugate base. Okay, so looking at the Ka chart, and I'm going to supply you with the Ka chart. Okay, so looking at the Ka of HCOOH, formic acid, it's 1.8 times 10 to the negative fourth. And then the Ka for the NH4, the other acid, over here on this side, it's 5.6 times 10 to the negative 10th. Okay, so this one is more soluble than this one. See, -4, -10. So this one is more soluble. Okay, it's stronger. So it's going to favor the forward reaction. So since this is stronger, it's going to favor whatever side this is on. So this is on the reactant side, so it's going to favor going this way, the dissociation of it. Now, if this was the stronger acid, then it would favor the other direction. Okay? So those are just some important facts that you need to know about Bronsted-Lowry acids. And for our last thing, oxides. So this is any oxygen that's bonded to another element like SO2, CO2, and NO2. So this is a covalent bond. All right, so we had to remember what covalent and ionic bonds are. Remember, ionic is a metal plus a nonmetal. Okay, this is two nonmetals, covalent. So sulfur, carbon, and nitrogen are all considered nonmetals. So this is oxygen bonded to a nonmetal. When you have oxygen bonded to a nonmetal, it's called a covalent oxide. Okay, covalent oxide. Covalent oxides, when combined with water, form acids. So we see SO2 plus H2O forms H2SO4. It's an acid, right? CO2 plus H2O, H2CO3 forms an acid. On the other hand, if you have an ionic oxide, if you have a metal combined with oxygen, then it's going to form a base. So sodium oxide, okay, combined with water is going to give you NaOH, sodium hydroxide. And if it's just oxygen by itself, like the oxygen ion, combining with water, then it's just going to give you OH, which is the polyatomic ion hydroxide. And then again, metal calcium oxide with water is going to give you calcium hydroxide. Okay, so these are just pieces of information that you need to retain, some factual information. The main thing about this section right here is writing these Ka and Kb expressions, because in our section 9.4, well, actually a little bit in 9.3, but especially in 9.4, we're going to start looking at calculating things with the ICE charts and knowing how to write these Ka expressions. So it's just like the KSP that we did, right? Just exactly like the KSP, except for now these are acids and these are bases. Same thing, products over reactants, the concentration of the products over the concentration of the reactants. All right, so that's it. Make sure you slap that like button right across the face. Give me a thumbs up, subscribe if you haven't already, and then make sure that you hit that notification bell so you know when I put up new videos on YouTube, and you can watch them quicker than what they appear in Google Classroom.